Hi everyone, my name is Aamod Khatiwada. I am a third year PhD student at Northeastern University, Boston. Today, I am going to present our work, Knowledge Graph Embeddings for Causal Relation Prediction. This is a joint work with Sola Shirai from Rensselaer Polytechnic Institute and Kavitha Srinivas and Oktie Hassanzadeh from IBM Research at Yorktown Heights, New York. And this work was done at IBM Research. Here is the outline of this presentation. I will start with the motivation behind this work. As we know, the news articles cover different events going on around the world. Following them, we can keep track of the current incidents. The figure here shows the number of news articles published about different news events around the world. For instance, this red bubble shows that there were 1,879 news articles about FBI raid in the former president's house. Concurrently, on the another part of the world, there was a flood event that was covered by 330 news articles. Such news events can help us to understand the current events going on around the world. So, if some events take place today and we want to know its possible consequences, we may analyze the consequences of similar events in the past, which can give us an idea of the possible consequences of the new event. So, in high level, we are working on a project where our main objective is to predict the future events based on the past similar events that are covered in the news articles. And to do that, we should keep track of the past events, and for this, we curate an event-related causal knowledge graph. Causal knowledge graphs store the news events as nodes and their cause-effect relations as edges. The figure here shows a simple causal knowledge graph. For example, the nodes earthquake and tsunami are the events, and the edges between them indicates that the earthquakes in the past had caused tsunamis. Note that the events can be in the top level, such as earthquake, as well as in an instance level, like 2015 Nepal earthquake. Also, there can be other non-causal edges like instance of and subclass of in the causal knowledge graph that helps to maintain its semantics. We use causal knowledge graph of past events to understand, analyze, and forecast consequences of the future events. However, like other knowledge graphs, causal knowledge graphs also face the problem of incompleteness. For instance, our sample causal knowledge graph does not contain a causal edge between volcanic eruption and tsunami, although it has been detected in the past that volcanic eruptions can cause tsunami. Therefore, we intend to study this incompleteness problem in this paper. Precisely, our objective is to find the missing consequences of the events in the knowledge graph. We are given a source event. We want to find the set of its top k effects or consequences. For example, given a source event volcanic eruption, we want to find its target events like tsunami, earthquake, structural failure, and so on. And for doing that, we use knowledge graph embeddings. Precisely, we want to represent the nodes and edges in the causal knowledge graph using their respective vector representation in an embedding space, such that the embeddings of the target events are the function of the source event and their relation. In our case, the relation is always the causal relation, such as has effect. The causal relation prediction task is a subset of link prediction tasks, and there are a lot of work that focus on predicting the target entity in the knowledge graph when the source entity and the relation is given. However, these work mainly focus on general source entities and the relations that have one possible target entity. For example, if Barack Obama is our source entity and birthplace is the given relation, then there is a single possible target entity, that is Honolulu. However, if we see causal relations, they are generally many to many. That is, same source event can have multiple possible target events having a causal relation. As shown in the slide, earthquake can have multiple target events like structural failure, tsunami, landslides, etc. There are many knowledge graph embedding techniques for link prediction tasks in the literature, but they have been evaluated for the general knowledge graphs and have not been explored for causal relation prediction tasks. Also, the existing link prediction benchmarks mostly contain general one-to-one relations between the entities in the knowledge graphs, but they do not have event entities, which are mainly many-to-many. So, based on these observations, we make the following contributions in this paper. First, we evaluate the existing link prediction techniques when they are used for the causal relation prediction tasks. Since the existing benchmark do not contain event entities and causal relations, we introduced two new causal relation benchmarks for our evaluation, which is our second contribution. Third, we also analyze the limitations of the existing evaluation metrics used for the general link prediction tasks when they are used for evaluating many-to-many causal relations. We also propose a novel manual evaluation strategy that helps to understand the performance of different techniques on causal relation prediction with reduced efforts. Now I will talk about the methods we use to find the causal relations. Since our problem is a subset of well-known link prediction problem, we evaluate the state-of-the-art embedding-based link prediction methods for finding the causal relations. Precisely, we use trans-E and Tucker among the linear models, complex among the semantic-based model that uses real and complex plane to distinguish asymmetric relations, conv-E among the CNN-based models, and we also use NOS, which is a recent GNN-based model. The selection of these models is based on their performance in the existing link prediction benchmarks. To the best of our knowledge, there are no any openly available benchmarks that can be used for the causal relation prediction tasks. Therefore, we create two new benchmarks for our evaluation. We use the events in Wikidata to create these benchmarks. However, there are no any properties in Wikidata that helps to distinguish event entities and types from other entities and types. Therefore, to identify the news event entities, we map the news headlines in Wikinews to the types in the Wikidata. Then, we consider the types having a mapping to the news headlines as event types. Using these mappings, we were able to identify 50 event entities like earthquake, landslides, etc. in the type level. We consider all such type level entities along with their instances as the event entities. Then, we extract the triples from Wikidata by ensuring that each triple contains an event as at least one of either head or tail entity. But to make sure that the benchmark is representative, we go one more hop away from the entities collected in the first round to collect triples of entities that are related to the event entities. The first benchmark only contains the causal relations in the validation set, so we call it WikiCB. The second benchmark contains the mixture of causal and non-causal relations in the validation set, and we call it WikiMB. We remove the inverse triples to overcome the leakage issues. Also, the performance difference in these two benchmarks will help us to understand the role of non-event related triples in causal relation prediction. Now, I will go through our experimental results. Before starting the experiments, we set two main empirical questions that we want to answer. First, we want to understand what is the best way to create the datasets for the causal relation prediction tasks. Second, we want to understand how the existing link prediction techniques predict on the causal relation prediction setting. For each method, we select the trend model that minimizes the validation loss. We perform our evaluation using MRR and hits at K for K equals to 1, 5, 10, and 50. We also report effectiveness based on our manual evaluation framework that uses precision and recall as metrics. So to begin, we first understand what are the best performing methods for the link prediction tasks in existing link prediction benchmarks. As reported by the previous works, NOS and complex are the best performing techniques, but not by a large margin. A possible reason for this technique to perform best is that NOS captures the graph structure better and complex can handle the asymmetric relations. Second, we want to understand if using the mixed validation set gives better result. So, we apply the same 5 techniques over the newly created WikiCB and WikiMB benchmarks. We observe that there is significant improvement in the performance of the techniques when we use mixture of causal and non-causal but event-related triples in validation set. So we concluded that it is better to use mixed validation set as it provides the negative examples for the model while learning the causal relations. Third, we report the best performing technique for the causal relation prediction tasks. We observe that NOS, which is a graph-based method, performs the best, followed by complex and conv. We also observe that linear models like trans-E and Tucker are not able to perform well because they use simple translation from the source in event to the target event, and they mostly capture the similarity between the events rather than causal relations. Although NOS perform the best, we observe that the absolute performance scores are very low for all the techniques. For example, here we can see MRR is only 0.032 and only 0.085 in WikiCB and WikiMB benchmark given by NOS. To understand the reason behind the low absolute scores, we analyze the results by each technique manually. There, we observe that the techniques are performing better than what metrics reported, but they are being penalized due to the incomplete ground truth. And note that it is impractical to create the perfect ground truth from the incomplete knowledge graphs having a lot of sparsity. This will need a lot of manual evaluation. For example, when we use nose, which is the best performing technique to find the top 1 consequences of earthquake in WikiMB benchmark, we get structural failure as the top result. But in the ground truth, we only have tsunami and landslides. Hence, the correct results are interpreted as incorrect results. As a solution, one can verify the results manually, but the manual verification is a lot of work. For example, even if we want to evaluate top 5 results in WikiMB benchmark having 1500 test cases, we should evaluate 37,500 triples. Therefore, we come up with a novel manual evaluation framework where the idea is to map the instance level prediction to their respective top level prediction and evaluate their correctness. For example, for these two triples, George Floyd murder has effect George Floyd protest, and death of Xavier Ordonez has effect Xavier Ordonez protest. Both of these triples are about murders and the following protest. So we map them to their respective type level and evaluate the correctness of murder has effect protest. Then we find top 10 target events for each seed event by each technique, which we use to create a relative ground truth. Over this ground truth, we report precision and recall. Note that since one source event can have many target events, we use precision and recall for the top K result evaluation. If you are interested in the further details about our manual evaluation framework, we would like to redirect you towards our paper. So we report the results when taking top 5 target events per source event. We observe that complex and nose are the winners again. Also, it is interesting that complex produces few results due to which its recall is low, but it is highly precise. Furthermore, the numbers are significantly high than what we expected or what we saw in the automatic evaluation. And this also supports the use of our new manual evaluation strategy. We also report the results on other values of K, which again shows nose and complex are the clear winners. Also, Talkers and Francie have good recall after K equals to 5. This is because they generate many prediction results and their correct predictions are distributed throughout the ranking order. On the other hand, since complex has most of its correct predictions compressed at the top, its recall drop after K equals to 6. This also shows that complex works better for the source events having less target events. All in all, we saw that all these techniques have their own speciality and they work better for the different part of the knowledge graph rather than a single technique working based in the entire knowledge graph. Furthermore, we also analyzed if we get better prediction results on applying the thresholds rather than using the top K rankings. So for fair comparison, we first generated top 5 results by each technique and apply a threshold over them. And we observed that there is a small improvement in the F score when we apply threshold over these top K results. As expected, the precision goes high for high threshold and recall goes up for the lower threshold. We saw that the recall gets saturated after certain threshold value, which shows that there may be a threshold value which gives optimum F score. This is still an ongoing work. We are still trying to explore this aspect. So our experimental analysis showed that the GNN-based methods perform relatively better for the causal relation prediction tasks, and using mixture of causal and non-causal but event-related triples in the validation set helps to select the best models. Moreover, we also observe that the methods make true predictions that are unique to each other. So this opens the door for exploring ensemble of these methods for better prediction result. So in the future work, we will also explore the threshold-based approach more to see if it can be the replacement of the top K approach. And I'm really grateful to everyone for listening to my presentation. Please feel free to visit my webpage for further details and do not hesitate to reach out to me through my email. And I will be happy to answer your questions if any. Thank you so much.